So now let's move to the full ladder and full subtractor, as I said. So these are some questions like explain the full ladder, design its truth table, express sum and carry in terms of mean terms and max terms. It's mean terms and max terms actually. Design its circuit, diagram using basic logic gates, and implement full adder using half adder. Okay, it's not a big deal actually. Now let's go through it one by one. What is a full adder? Full adder is an adder which adds 3 input and produces 2 outputs. The first 2 inputs are A and B, and the third input is an input carry as C in. The output carry is designed as C out, and the normal output is designed as S, which is sum. So this is the full adder actually. Here there will be, as I said, there will be 3 inputs A, B and C in, and the outputs are sum and carry, which is carry out. Now, as I said, before we designing the circuit, we need to do the truth table first. So now let's do the truth table. There will be 3 input, which means there will be total 8 combination will come there, and you have to write the sum and the carry out like the before we done in the half adder. Okay. Now then after that you have to do the logical expression for sum. Logical expression for sum that can be taken from here itself, or you can use KMAP, right? If you have a truth table, you can take it from here itself, no problem. Which means further simplified using KMAP, but for half adder and full adder, as we are constructing using AND gates, it is easier when you do it with the truth table only. So you can get the truth table from after solving this. For the sum, you get for the sum as C XOR A XOR B, right? C in means it's nothing but the ABC, that's C. C in XOR dot A XOR B. Then from C out you get as right AB plus BC plus AC. Okay, but this AB plus BC plus AC can be implemented in another form as AB in the C plus 1 and AB in C plus A complement B in C. And after we get as what? AB plus C into A XOR B. Because I suggest you to do this, because when you get AB plus BC plus AC, when we construct while we using the construct using the NAND XOR and NAND gates, we take, you see that we take from here. Okay, we take from here, which means it is A XOR B, and it is AND using what? AB. Okay, then you use this thing C into XOR B plus what? AB, you get the output. Okay, while using this you may not get the predicted output as for the implementation, insert implementation. So I suggest you to study this thing. Okay, means we need to get the C out as AB plus C into A XOR B. AB plus C into A XOR B. Now let's see how to implement this. As we said, the sum is A XOR B XOR C. So we use an XOR gate here from AB. So we get an A XOR B, and another C goes through here. So which finally comes output as A XOR B XOR C. Then we need what? Then we need an C out. What is the C out? C out is C into A XOR B plus AB. For AB, we can use what? The AND gate. So we take from A and B, we get through AND, the output as AB. And what is the real output? AB plus C into A XOR B. So for that we take from here. Here what is the output? A XOR B. And from here we get the C. And the final output from this AND is nothing but A C into A XOR B. So from here we get C into XOR B. From here we get AB. Final output is C into XOR B plus AB. Simple as that. So this is how we construct the full adder. Now Let's study how to construct the full adder using the half adders. Okay, how to construct the full adder using the half adders. So here it is a simplified implementation. We need two half adder pin and an OR gate to implement the full adders. Two half adder and an OR gate. Okay, from this half adder the sum is passed as an input to the next half adder. Okay, then we take the sum as the sum, and the carry and this carry is added to get then another the resultant full adder carry. Okay, once more we use the two half adders and an OR gate to construct a full adder. Okay, now let's construct this using the logic gates. For that I had it, but I will give you as an assignment. It's actually easy. You have to construct a half adder here and a half adder here and connect the sum to the second input of the half adder. Okay, one input of the half adder. For the first input, connected the C in. Now the C out came from here and the C out came from here. Two half adders connected to the OR gate to make the resultant C out. Okay, that's it, very simple. Now let's do the full subtractor and implement the full subtractor using the half subtractors. Let's see how can we do that. So let's see here, what is a full subtractor? That can be asked for as a question for the definition. So we can study as a full subtractor is a combination circuit that performs subtraction of two bits. One is a minuend and the other is a subtrahend. Taking into account of borrow of the previous adjacent lower minuend bit, this circuit has three inputs and two outputs. So as I said, the one input will be the two inputs will be A and B, the ordinary inputs. Then the third input will be the borrow of the previous adjacent lower minuend bit. Okay, so hence we have three inputs like A, B and B in and two output. You know what the two output is, just the difference and the borrow, B out. So this is how it is constructed, implemented as a simple implementation, A, B and B and a full subtractor which comes as a D and B out. Now let's construct the truth table. You can take a look and use your pen and paper to construct the truth table your own. And if you have any doubts, please put in the comment section. From this we can construct the K-map. For the full adder, we didn't construct the K-map, right? We can construct the K-map, but we can construct the K-map actually. Here we just using the K-map for easy implementation. Here only, full adder also we can use the K-map. You guys don't need any confusion. I always suggest use the K-map. Okay, that's the standard way of doing it. First truth table, then the K-map, then the design. That's it. So from the input and output you can construct the K-map like this. For here the D is enabled 1 2 3 4 times at where 0 0 1 0 1 0 1 0 0 and 1 1 1. So 0 0 1, then 0 1 0, then 1 0 0, then 1 1 1. So as they are not adjacent, we have to take like this. So finally we get A bar B into C plus A B C, which is it is nothing but A XOR B XOR C. A XOR B XOR B in. Okay, this is a standard equation for the A XOR B XOR B in. This is XOR B XOR. It's the expansion of A XOR B XOR C. And here from the output we get as A XOR B, then A XOR C, means this B in is C, A XOR B in, then A XOR B and B in. Okay, this is just a logical expression. As I said, for the D you can construct it as A XOR B, then XOR B, A XOR B XOR C, A XOR B XOR B in. Sometimes I use C, sorry for that, it is nothing but B in. Okay, So this is for the borrow thing. Okay, ax or b plus ax or b in plus ax or b, then b into bn, which also can be implemented as like this: b in into ax or b whole complement plus a complement b. And you guys ask why we do that. Because for the logic circuit of the full subtractor, we use this method for doing. Okay, so let's see how we construct the logic circuit. First we need d. What is d? Ax or b xor c. So we take a b and in the xor gate it becomes as a x or b, and another the b in will come through this, and it is xor with this xor gate, and the final input will be x or b xor c through the difference. Okay, then what we need? Then we need for b out b in into x or b complement. For that we take from here we get b in, from here we get the ax or b whole complement. So by AND gate we will get the final output as b in into ax or b complement. Then we need an another thing, that is a complement into b. For that we take a b from here and the complement of a from here, and we multiply using the AND gate, then we get a complement into b. Then we put in an OR gate for this plus thing. Finally we get the b out as b into x or b whole complement plus a complement b. Please look through this statements and use a pen using a pen and paper. You guys please do this yourself, then only it will be understood well. Okay, don't just by heart the circuit itself, because there is a lot of complex circuits coming up, so you cannot just by heart them. Please study the process very well. Okay, now for the final touch, for the next thing we have to implement the full subtractor using the half subtractors. Then after this we will study to how to implement the full adder and half adder using NAND gates only. That's also there, it's not in the given slide. I will put another slide and show you guys how it can be implemented. So look at here, implementation of full subtractor using half subtractors. It's actually easy. We have to use two subtractors and one OR gates, and later we use two half adders and an OR gate for full adder using half adders. Here the symbol for full subtractor using half subtractor is also like the same. Here the final carry is connected to the carry element. There was carry, here it is borrow. So that borrow is connected to here, and this input, this AB output is connected as the input, as one input for D, and here it is directly connected, and this one extra C is connected to the B in. Okay, it's easy. That's how we can construct the half and full adders and half adder using, half full adders and full adders, and full adders using half adders and the full subtractor using half subtractors. Next we will study how to construct full adder and full subtractor using NAND gates only. Thank you.